Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to continue whatever we have done or whatever we have started in the last class, which was about the design of a two-way slab. And we said there are certain things that we need to check for while designing for a two-way slab. And we have said there are different steps involving, first we need to check whether it's a one-way or two-way slab. Why? Because once again, in one-way slab we are having one major bending, and two-way slab we are having two major bendings. The tables which are used for one-way slab are different from the tables used for two-way slabs. So that's why first you need to verify which type of slab is there. Now, in advanced RC design, you are supposed to be having only two-way slabs, but once again, it is very important for you to know how to check. After that, we said in two-way slabs, we have two types of conditions or two types of support conditions. One where it's simply supported, and the other one where it's continuous or restrained. So there is a small table for the simply supported, there is a big table for the restrained. And then we need to know how to check the materials, if it's given in the question, if it's not given, how to get them from the code. So I assume I have already taught you how to do it. And then we check the actual failure, so actual failure possibilities. And we said normally a slab can fail, or an RCC element can fail in different modes. One is durability, another one is bending, another one is shear force, or area of reinforcement, shear reinforcement, and then finally deflection. There are certain steps which you require to do as well, like for example estimation or calculation of effective depth. In order for you to calculate the loading, after that you will be able to calculate only the bending moment. So we have reached at that day to area of reinforcement, and we have got the values of K, if you remember, Z, and then finally we have got the values of AS. And we said that we have three ASs. We said that we have something called the minimum, we have something called the required, and we have something called the provided. The required is the amount I require in order to resist bending, while the minimum is the lowest possible amount. The lowest possible amount to avoid any cracking. Provided is the amount we keep, and always we keep values corresponding to the available sizes of bar. So we have, for example, 8, 10, 12, 14, 16, and it goes on. I cannot have, for example, a diameter of bar which is 15.4. It is not there in the market. So I cannot have any area. Your area should be corresponding to a diameter size. That's why there will be a required and there will be a provided. Okay. Required is the amount I need, okay, exactly due to the bending moment. Provided is the amount that I'm going to provide, which is going to resist the bending, but in terms of the available bar sizes. Are we clear for this point? Are we clear about this point till now? Any question about this point? Okay. And then after that we said there are two ways of finding the provided. We said either you go to the table or you find the area manually using the concept of finding the area of one bar multiplying by the area of bars, and you can find the area, you can find the number of bars, area of one bar multiplied by the number of bars. Okay, and number of bars can be found as 1000, which is the width that we are designing for, divided by the assumed spacing. So you start the assumption of spacing to be 300. After that, you will go, if 300 is not sufficient, you will go for 250 or 275, 250, 225, 200, and it goes on. Whenever you let the reinforcement be closer to each other, you will see that the number of bars will be more. Okay. If I have 5 bars, then the spacing is 1000 divided by 5 will give me 200. If I let the spacing go smaller, once again the number of bars goes higher. If I let the spacing between the bars to be 125, so 1000 divided by 125, that will give me 8 bars. So once again, when the bars are going to be, the bar spacing will be smaller, you will see that the area is going to be higher because the number of bars is going to be higher. Today we are going to start the next check, which is about shear reinforcement. Now, in order for us to start the shear reinforcement part, first we need to understand the concept of shear reinforcement. Now, if you remember in bending moment, we said that assuming that this is going to be my element, the drawn element, for example, you will see what happens. Assuming that we are having a distributed load, okay. Now we said we need for the bending moment, we require to know the type of support, whether we are talking about a discontinuous support or we are talking about a continuous support. So you will see, if this is going to be my bending moment envelope, you will see that this will start at 0 because it's discontinuous support. It goes up because of the continuity from both sides, up, 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 and then finally it goes to 0 because it's discontinuous. Now this is something that we have learned already for a bending moment. And then if it's a two-way slab, you need to do for both sides, okay, both directions. Now, for shear force, you will see that whenever we talk about shear force, we are talking about going up and going down. Okay, we are talking about the matter of going up and going down. Now you can see this particular support, assuming that this line that I have drawn, the one here, is representing a paper. Okay, so I'm having a paper, and I'm trying to say that there is a reaction here pushing my paper up. So you will see that this particular paper is going to be raised from this side. Now you can see that there are loads coming, or loads pushing my paper down in this area. So you can see first they will try to push it down, and then once again it's continuous, so it keeps pushing my paper down till it reached to a certain position here. Now once again, or let us make it a bit accurate, or let us make it correct. Okay, so it takes so we went up because of the reaction, we went down because of the load. The load keeps on going down till we reach to the end of this span. Now at the end of the span, there is another load going to take you up. So once again, this is going up. Once again, there is another load taking you down. So I keep on going down. there is another load taking you up. So you will see that the pattern of shear reinforcement is going to be of this shape. It's a matter of going up and going down. It does not relate to whether the support is continuous or discontinuous. The support being continuous or discontinuous will affect your bending moment value. In case of discontinuous, then it's having a bending moment of 0. In case of continuity, the bending moment is going to be there. In case of shear force, in both scenarios, whether you are talking about discontinuous or continuous support, you will see that your shear force is still there. There will be a reaction. There will be a value of reaction. Okay. Is it clear about drawing the bending moment diagram? Once again, reaction will take you up, load will take you down, up and down till we reach. Now, if we are having something like this, for example, you will see that your shear force diagram, because of this reaction, and we are having our paper, you will see that the paper will go up. Now, in this scenario, there is no load, so you will see that there is nothing happening. My paper is going to remain the same. Now, there is a load taking me down, so I'm going to go down. Okay. Now, of course, whether it goes above the reference line or below the reference line, that depends on the intensity. But this is the typical shape of shear force diagram. Now, in this region, once again, there is no load, so it goes straight. And then finally, we have our reaction, which will take me up, so I went down. Are we clear about the shear force diagram? Any question regarding the shear force diagram? Now, when it comes on slabs, we don't have a system of point load. Everything is a system of a UDL. So always you will see that your shape is corresponding to this shape, whether it's discontinuous and continuous. Once again, we say it for continuous and discontinuous, it will affect your bending moment, because in the discontinuous, the bending moment is 0, while in the continuous, there is a value of bending moment. Now, for shear force, both discontinuous and continuous are having reaction values. So I cannot say any one of them is 0. Are we okay? Any question about this?
We understand.
Okay. So we'll go to the shear force directly then. Going to the shear force. You will see that this is my slab. This is my slab. You will see, as we said, we are drawing the reference lines, like whatever we have done for the bending moment. Now we are going to plot the shear force diagram. Now you can see that my shear force, as we said, it is going up because of the reaction, because of the location of the beam. Or we can say that there is a beam here, so of course because of the reaction of the beam it went up. And then there is another reaction here, that's why it went up from this point to here. Now, what about this? This is representing the UDL available in this slab. The UDL will take you down. Okay. So up because of the support, down because of the loading, and then once again up because of the reaction. The same thing goes for the second scenario. Okay, the same thing goes for the second scenario. Oh, the same thing whatever we have done for bending moment, if you remember the equation, the general equation of bending moment was moment equals to beta WLX squared. And from where we brought this one? We brought it as an example of moment is equal to WL square over 8. And if you remember, we said it is going to be 1 over 8 WL square. And we said 1 over 8 is our coefficient of bending moment, where W is W, Lx is L. Now, if we see now the equation of shear force, if you remember, the equation of shear force is WL over 2, okay, which is going to be half of W into L. So if I want to get the general formula, then I can say then my V is equal to beta. Now to differentiate between beta moment and beta of shear, we just write PV. V is representing shear force. So we have beta, which is half here, multiplied by W, multiplied by L. Now it's not Lx square, it's only Lx. Are we clear about the general formula of shear force? Once again, depending on your depending on an equation of bending moment or shear force, you can develop your general formula of shear force and bending moment. Now, what do we require in order for us to calculate the shear force? We require to calculate beta, we require to calculate W, and we require to calculate or check for L. Now, Lx we have already found, or Lx has been given in the problem. W we have calculated it in the last class. The remaining thing for us is going to be the value of beta V. Now we have learned that there is a table for the bending moment coefficient. What about the shear force coefficient? Now once again, if you go to your BS code, which is the extracts or the general one, and we went to the table of contents. In the table of contents, I'll be searching for something related to shear. So you can see that shear reinforcement is mentioned here. I'm just clicking on the shear reinforcement, and they have told me that there is shear stress of the load, where your stress equals to force divided by an area. So we have shear stress is equal to shear force divided by the area of shear. And you can see once again there is a table here. Okay, there is a table here, and you can see here we have the same conditions that we have used for the bending moment. So the same 9 cases. 4 edges continuous, which was interior, and then one short edge continuous, one long, 2 edges and edges. So the same conditions that we had in the bending moment coefficients. The only thing, whatever we are having right now, is only the shear force. Now in our problem, if we see in our problem, it is 2 adjacent edges discontinuous. We have 2 sides which are discontinuous. One is long, another one is short. If I'm being fast, or if you didn't understand anything, let me know. Okay. Now you can see here, for 2 adjacent edges discontinuous, once again we have beta V for X and we have beta V for Y. Once again, beta V for X depends on the value of Ly divided by Lx. Beta Vy will not be depending on that. So now if I try to find my coefficients, you can see that for beta Vy, my coefficients are 0.4 and 0.26. 0.4 is representing the continuous edge. 0.26 is representing the discontinuous. So now if I see the X, this is my drawing of X. You will see that X is having one continuous part and one continuous part. Now for the discontinuous, which is here, you will see that your coefficient is 0.26 because it's only carrying a certain slab from one side. The other one is going to carry from both sides, so this is going to be, of course, higher. So my coefficient here is going to be 0.4. Okay. The same thing goes for, this is not for X, this is for Y. So this is going to be 0.26 for Y, and this is going to be 0.4 for Y. Now what about X? Once again, if you remember, our Ly over Lx is 1.25. And we said 1.25 is in the middle of 1.2 and 1.3. So we need to get the average of 1.2 and 1.3. You can see the average of 1.25 is going to be 0.4825 for X. For X continuous, and for X discontinuous it is 0.32. So here we are having 0.32 and here we are having 0.48. So now we have found the coefficients of shear for both x and y. We have our W, we have our Lx, then we can go and calculate for our shear. Okay. Any question regarding finding the coefficient? It is the same process, but rather than using the bending moment table, you are using the shear force table. Any question for the meantime? Or are we fine?
No question, Mr. Thank you.
Okay. So now if you see, we have the four coefficients. If we return back to our code, the code says first that the equation for shear stress is V divided by V capital, or V capital divided by V into D. And I think I have explained for you why we are using D small and not D capital. Did I explain for you or did I explain for the other section? Because one student has asked me why we are using D small, not D capital. Is it from this section or from the other section? Do you remember that I explained why D?
No.
Okay, so can you just guess why we are using? First, what is the equation of stress? What is the equation of stress?
Force by area.
Okay. So we have a general equation of stress equals to force divided by an area. Now we have different types of shear. Different types of stresses. We have something called shear stresses. So in that, what we are going to have, shear stress is going to equal to shear force divided by the shear area. Okay, or let's say AV. Now, this one, when it comes to shear, we are just denoting it by a small v. So small v is equal to v divided by AV, which is, in this scenario, B into D. Now, there is another stress, which is whatever we call it then as normal stresses. And normal stresses can be either of tension or compression. Okay, we can have tension stress, we can have compression stress as well. And then the last option, whatever we have it as flexural or bending stresses. In which you have studied in mechanics of materials, I believe, where you had the equation of stress equals to my divided by I. Do you remember this? Do you remember this? Now where your Y is D over 2, which is half of the section, and your I is BD cube over 12. Now if we have I over Y, then it's going to be BD cube over 12 divided by D over 2, which will give you BD square over 2. Okay. Now this BD square over 6, you had it as Z. Now this is I over I. Now if we have like our case, which is Y over I, and your Y over I is going to be 1 over Z. Okay, 1 over Z. So now if I multiply M multiplied by 1 over Z, then it's going to be M over Z. Okay, so that's going to be the flexural stress as well. Okay. Now in this scenario, why do we use D small? If we are saying that it's an area, we know that area is equal to width into depth. If we are having a section which is having a width of B and a depth of D, then the area in this scenario is B into D capital. Okay, B into D capital. So why we are using D small and not D capital? Any person? Can you try? You have used this equation for a long time, for a lot of semesters. Can you try to guess why it's D small, not D capital? And you should ask yourself always. Now, if it's a stress which is force divided by an area, we know that force can be a shear force, so that's why it's D capital. Area is area, means width into depth. Now, if it's width into depth, why I'm using D small and not D capital?
Maybe this is effective area.
What do you mean by effective area and why?
The
Why,
area
like for example, why in calculation of minimum area, you remember AS minimum? We have used 0.13% B into D capital. Why in self weight? We have used 24 into D capital, not D small. Why in shear we have used D small? Any person? Okay. Now when it comes to shear force, now let us assume that I have a section. This is my section where reinforcement is available. This is my reinforcement. Okay. Now shear tries to, or because of the loading, shear is going to start having a crack. Okay. So because of the loading, crack will be developed. Now what are the things which will protect you from this crack? What are the layers in your concrete which will protect you from this crack? Now there are three layers. Layer number 1 is fast concrete and compression. So if we assume that this is my neutral axis and this is my tension zone, this is my compression zone. Okay, you can see that the concrete in compression is going to be at the top. So first, the crack should be this area, which is concrete in compression, because concrete in compression is strong. Now, if the crack is strong or the loading is high, you will see that the cracking is going to start or is going to continue. Now after that, we have a barrier. Okay, we have the second barrier, second layer, which is whatever we call it, aggregate interlock, where aggregate gathers. So if we see here, you will see that this is the position normally where a lot of aggregates are going to be gathered. Now, of course, the load will not be able to break your aggregate, but you will see that the load, if it's strong enough, it cuts between the weak layers, which are, or weak points, which are between the aggregate. So now, if the loading is huge, you will see that it will beat the concrete in compression, represented by your cover, and then the aggregate interlock, which is the position where the aggregates are accumulating. Now, if it went because of the height, again, can you mute yourself, please? Okay. Can you mute yourself? Okay. Now, you will see that there will not be any barrier in this area. Okay. There will not be any barrier in this area because we said concrete is weak in tension. So the concrete is not going to stop me in this area. Now you will see the crack will be penetrating this area easily till it reaches to the last barrier. The last barrier is what? The last barrier is your steel and tension. Now if the crack caused by the shear force is huge and it cuts or penetrates your bar, what will happen if it reaches to half of the bar? You will see that if you reach to half of the bar, by the own weight of the bar will bend down, or it will go to the lower side. Now anything from this area will not provide you any kind of barrier for the cracking or for the shear. Half of the bar is already lost because you have already lost the first half. The second part, which is the cover, but it's acting in the compression or in the tension zone, and we said that concrete is weak in tension, so that's why it cannot resist your cracking. It means that the part which is going to be protecting my shear is going to be this part. It is going to be this part. The other parts are not going to be protecting my shear. Now what is this part? This part is your B, which is your width, and this is going to be your B small. Is it now clear why we are using B small, not D capital?
Yes.
Okay. Returning back to our problem. You can see, first, in order for us to calculate the shear stress, we need to get our V capital. And we said our V capital, or shear force, is equal to beta multiplied by N or W multiplied by Lx. Okay. So we just multiplied using the coefficients. 18.56 was our load, Lx is our shortest span, and we multiplied by the coefficients. You will see that we have got 4 values because there are 4 coefficients, 2 for x and 2 for y. Now, for bending moment, we need to design the reinforcement. Since there are 4 bending moments, there will be 4 reinforcements. Now, for shear force, I don't need to provide shear reinforcement because we said already that slab is going to have a smaller loading per point or per location. That's why normally it's going to be singly reinforced as whatever we have said in the last classes, and it's going to be as well case number 1 of shear reinforcement, where you don't require to provide any shear reinforcement. In this scenario, we don't need to provide reinforcement, so only we need to check whether there is a requirement or not. So among the 4 of them, I'm going to choose only the highest one. Why to choose the highest one? Because if the concrete is safe to take 36 kilonewton, then it's safe to take 29.7, 19.3, and then 23.8. So only due to the checking purposes, you will be only taking the highest one. If the highest is safe, means the others are safe. So now you can see, this is my highest. I'm going to find the shear stresses now. My shear stresses is going to be, or shear stress is going to be V capital divided by V into D. Okay, where V is 36. Now my B is 1000 or 1 meter. And my D, now I should know which D to be used, whether it's Dx or Dy. And you can see in this scenario, which coefficient we have used. Is it the coefficient of X or is it the coefficient of Y? It is the coefficient of X, so it should be resisted by the reinforcement of X, which is represented by Dx. Okay, so since it's X, we have used X here. And you can see that we have got our shear stress value to be 0.24. Now this is the amount of shear stress caused by the load, because we have taken the load into account. Now I need to check the shear stress which can be taken by the concrete section. And once again, what is the concept of providing shear reinforcement or not? The concrete itself can hold up to a certain limit of shear. The load will cause me shear stress as well. I need to compare between how much the concrete can take and how much the loading is having. Now, if your loading is stronger than your capacity of the section or the section, you will see that it will cut it. If your loading is stronger than the capacity of the section, it will cut it. It's like a knife. If your knife is stronger than the element you are cutting, then it will cut it. If your knife, which is the loading, is stronger than the element, then it will cut it. In that scenario, I need to provide extra reinforcement as protection. Now, if the knife or the loading is something smaller, it cannot cut my element, then no need for me to provide extra reinforcement. So now we have our shear stress of the load. We need to get the shear stress of the concrete. And then we compare between them to check whether we require or not. Okay. So now, how to find the equation of shear stress for concrete? Once again, we'll return back to the code. Now you can see that for shear reinforcement, there are 2 points mentioned here. One is shear stress of the load. Another one is shear stress of concrete. Okay, so it says for you shear reinforcement or shear stress. It should be shear stress, not shear reinforcement. Shear stress of the concrete, and you can see here for the shear stress of the concrete, there is an equation of VC, okay, which is equal to 0.79 divided by gamma m, which is a factor of safety for shear reinforcement, multiplied by 100 AS divided by BD to the power of 1/3 multiplied by 400 divided by D to the power of 1/4. Okay. Now you can see that this equation is available in the code in this form. So this is my equation. I just rewritten it for you in that way. Okay. And it says for you allowance has been made in these figures for a gamma m of 1.25. Now from where we have got 1.25 for gamma m, or factor of safety, you can say either from note number 1, or you can relate it to the place of factor of safety for the materials. If you remember, we have used, or I have explained for you, the factor of safety for the reinforcement, that sometimes it's 1.05 for 460 and then it's 1.15 for 500. Now there is another factor of safety for shear reinforcement. Okay. So it says for you shear strength without shear reinforcement 1.25, because till now we didn't provide any shear reinforcement in the section. So the factor of safety is 1.25. So either you get it from this table, or you get it from the from note number 1. So once again, we return back here. This is my shear stress of the load. Okay. This is my shear stress of the load. This is going to be my shear stress of the concrete. So we have 0.7 divided by gamma 100 AS over BD divided 100 AS divided by BD to the power of 1/3 multiplied by 400 divided by D to the power of 1/4. Now we know gamma M is equal to 1.25. Now which D to be used? I know that the D to be used is dx because your V is corresponding for x. Now other than that, they are asking us for AS provided, but there are 4 AS provided. There is ASX negative, there is ASX positive, there is ASY positive, and there is ASX X positive, X negative, Y positive, and Y negative. Now which one to be used? That should be found here. Now if you see in this particular figure, if we see this particular figure, let me just try whiteboard so to be clearer for you. If we are assuming that this is my section, or this is my slab, which is discontinuous on this side, and then here continuous, here is continuous, here is discontinuous. Now if I try to draw the shear force diagram, okay, let us start by the bending moment diagram. For the bending moment, it goes like this. And then we are going to draw another one for shear force. Now you can see that my bending moment goes like this. Okay. Where we are having this one as my X positive and this one as my X negative. Okay. And then once again we are having our moment here in the Y direction or the longer direction. And you can see that this is going to be your Y positive and this is going to be your Y negative. And once again for shear, what to do? We're going to draw, you can see that it is going in this direction. The sign convention here, it's not important. You can draw it this side or that side. Now this is the discontinuous part. This is discontinuous of X. This is the continuous of X. The same thing goes for Y. This is the discontinuous of Y. This is the continuous of Y. Now, from the values which we have got earlier, we have found that the coefficient of shear for X is 0.485. Or let us not write it in terms of coefficient, let us write it in terms of shear force directly. Okay. So let us go here. Okay, so we have shear force in this area for continuous of X, 36 kilonewton. For Y, it is 23.3. For continuous of Y, it is going to be 29.7. For discontinuous of Y, It is 19.3. And we said we are going to pick the highest value. So the highest value corresponds to continuous of x, which is the location here. Now this location corresponds to which moment? It corresponds directly to the moment of x negative. Okay, so we are talking about moment of x negative, and this moment of x negative has given you which area? Which has given you ASX negative. Okay, so you need to check your shear force that you have taken, or the maximum value of shear force corresponds to which bending moment, corresponds to which area of reinforcement. And you can see, if we go back, the area of reinforcement for x, how much we have found it. For example, here I have provided 350. Or in your case, if you are using the table, it will be 393, I believe. Okay, so in my scenario, I picked it using the equation, which is 350. So now if I go and check the value of V for concrete, you will see that I have used 350. So once again, how did we choose the area of reinforcement? According to the corresponding location of the highest shear, you will see that the highest shear is located where? You will check for the maximum bending moment. Maximum bending moment will give you which area of reinforcement. Now we multiplied these values and we have got 0.497. So we said that the shear stress which can be taken by the concrete is 0.497. But there is another thing written in the code itself saying for you so this is my equation, but there is something mentioned here that 100 AS over BD should not be greater than 3. So can we check? 100 AS over BD, this is 100 AS over BD, it is 0.233, so it is lesser than 3, that's fine. And then they told us 400 over D to the power of 1/4 should not be lesser than 1. So once again, if we go and check, you will see that 2.6 to the power of 1/4 will not give you 1. Okay. We have got this value, but once again the code says for you, for characteristic concrete strength greater than 25, the values in this table may be multiplied by FCU divided by 25 to the power of 1/3. The value of FCU should not be taken as greater than 40. Now what does it mean? It means that this equation and this table has been done only for grade of concrete 25. If I'm using more than grade 25 in my problem, then I need to modify the equation to fit for that grade. Once again, the grade and the table which are available, the equation and the table which are available here are fitting for or have been made for FCU 25. If it's more than FCU 25, then you need to modify your equation. Now, how to modify my equation? They said you need to multiply the values that you have got from the table or the equation. Okay. You can see that the values in the table are derived from this expression. So either the values from the table or the equation, okay, to be multiplied by FCU divided by 25 to the power of 1/3. It's like we are multiplying by cross multiplication our grade of concrete divided by 25, which was the original grade. You can see what I'm going to do. I'm going to take this 0.497. I'm going to multiply it by FCU divided by 25 to the power of 1/3. What was the grade of concrete for us? It was 35. It is more than 25, so I need to modify. So now I'm saying for you, after taking all the things into consideration, I have found that the concrete can take a shear stress up to 0.556. The maximum shear stress the concrete section in this problem can take is 0.556. It is a combination of both concrete and steel. Now, how much is the load over there? You can see that the load is causing you a shear stress of 0.24. So we have 0.24, and we have the maximum shear stress, which is, or we have the concrete shear stress, which is 0.556. So the load is weaker than the concrete. The shear stress of the loading is weaker than the concrete. It means it will not be able to cut it. So once again, 0.24, which is for the load, is lesser than 0.556, which is for the concrete. And in this scenario, if the concrete is already strong to take the loading, then there is no need for me to provide any shear reinforcement, like the example of the knife. Okay. If the knife is not strong to cut my element, then no need to provide extra reinforcement. And you can see we have solved in this problem. We have found out that it is singly reinforced and no shear reinforcement is required. And I told you from the beginning, this is due to the loading in a slab. Okay. So if you are finding it to be doubly reinforced, or if you are finding it to be having shear reinforcement or requiring shear reinforcement, then you have done something wrong in the calculation. Okay, you need to recheck your values. Doing that, we have checked for shear reinforcement, and it's appearing that we don't require shear. Okay, we don't require shear. So now, what we have checked, we have already provided the reinforcement. We have checked for shear. We have checked for durability. We have checked for minimum and maximum area of reinforcement. The last check is for deflection, which is the critical check. So we are going to go for deflection. Now, how deflection is measured or calculated in DS code, it is measured in terms of span by depth. Okay, it is measured by span by depth. If you remember, we used to have span by depth ratio. Okay, there is a certain ratio, there is a certain limit for you. Okay, now if you see here, actual span by effective depth, for this problem, the actual span by effective depth is 4,000 divided by 150. 4,000 is going to be my span, my short span, and then effective depth is going to be the short span as well. So we are going to have it as 150. So 4,000 by 150 is going to be 26.67. Now I want to check what is the maximum or the limit span by effective depth. And how to find that? My span by effective depth is going to be equal to ratio, but we said we are going to multiply it by a modification factor, if you remember. Okay. And this modification factor, we have assumed it at the beginning, and we said it's a trial and error. We are going to assume a value of modification factor, and then later we are going to check whether that value of modification factor is fine or not. And we said we start our assumption from 1.3 to 1.4, if you remember. Now we need to calculate the accurate modification factor. So what we need to do, we are going to get something called limiting span by effective depth. Now this limiting span by effective depth is equal to what? Is equal to modification factor into ratio, as I said for you. Now which modification factor is the new one, or the accurate one, or the actual one? Once again, the one we have used from the beginning was the assumed one. It's a trial and error. So we assume a modification factor to get the depth. At the end, we are going to check what is the actual modification factor and what is the actual span by effective depth possible. So now if you see, if we go to the code once again, if we go to the code, going for table of contents, now going searching for shear, going searching for deflection, going searching for deflection. So deflection requirements, you can see these are the ratios. The ratios will not be affected. The thing which will be affected is a modification factor. So now you see, we have assumed our modification factor to be 1.3 to 1.4. And they have given us the modification factor here. they have given us that the modification factor is having this equation. It depends on moment B and D square, and it depends on Fs, which is service thrust. Now, we didn't calculate service thrust previously. Now, this is going to be the equation of service thrust. Okay. Where now it says for you Fs is equal to 2Fy, 2 into grade of steel multiplied by AS required, divided by 3 AS provided. So it's we are checking how much utilization of steel is there in that section. Okay. Multiplied by 1 divided by beta B. Beta B is representing the moment redistribution factor, if we are having any redistribution factor. Okay. So it says for you here, if you see the percentage of redistribution. Normally we are allowing certain redistribution, or the code allows for redistribution of moments, but it's not recommended normally unless you require. Your task is to go and search for redistribution of moments. If there is time, I'll explain for you at the end of this session what's the meaning of redistribution. We have something called moment distribution, that's different, and we have something called moment redistribution. Okay. Now we know that we have two equations. One is equation 7, another one is equation 8. One is for modification factor, another one is for Fs. If we see here, this for us limiting span by effective depth is equal to modification factor into ratio. Now Fs is equal to 2 into Fy into As required divided by 3 As provided. Okay. Now, which area of reinforcement you will be taking? You will be taking the highest. Okay, the highest area of reinforcement. You will be checking whether that highest area of reinforcement is sufficient to control your deflection or not. Okay. So you can see that 2 multiplied by Fy multiplied by As required. If you remember, our As required was 315 for X negative, and then the provided is 350. If you remember, we said 314 is not sufficient. That's why we have taken 350 or 393 if you are going to go for the table. Once again, see it here. You can see that AS required is 315. And we said we are going to provide how much? We are going to provide 350 if you are using the equation, and 225 millimeter spacing. If you are using 200, then you can see that the table will give you 393. Both answers are correct, as I told you last. Okay, so we have got the value of Fs to be 276 Newton per millimeter square. Now you can see that the unit of AS will go with the unit of AS. The remaining unit is going to be the same unit of Fy, which is Newton per millimeter square. So this is millimeter square, this is millimeter square, this will go with this. Remaining is going to be the unit of Fy, which is Newton per millimeter square. Now after finding Fs, we need to find our modification factor. So our modification factor is this equation, which is 0.55 plus 477 minus Fs divided by 120 into 0.9 plus m over bd square, which should be, it is x because we are using the reinforcement of x. So according to whatever we have calculated, or according to whatever substitution is there, we have got our modification factor to be 1.496. And once again, you just notice that we multiplied m by 10 to the power of 6. Why? Because once again, Fs is in Newton per millimeter square. In short, wherever you see the value of bending moment, make sure that it is in Newton millimeter. Make sure that 2 multiplied by 10 to the power of 6. Okay, so we have got our modification factor to be 1.496. If you remember, we have assumed it at the beginning. Okay. Now here in this problem, it was not assumed. In the previous problem, We assumed it to be 1.3. In this problem, we have got the depth given as 175. And from the depth given, we have calculated dx and dy. Now, this is our modification factor, which is 1.496. Now, limiting span by effective depth is equal to modification factor. My modification factor is 1.496. My ratio is 23, and I'll explain why it's 23. So if we multiply these two values, we are going to get 34.41. Okay. Now you can see your limiting span by effective depth. This is the maximum limit that can I have. The actual span by effective depth is going to be this much. Okay, it is going to be this much. Now you can see that your actual is lesser than your limiting span by effective depth. What is going to be safe? Now, if I want to go and check or make it a bit simpler for you to understand, you can see that now if we multiply 26.67 into 150, it will give you how much? If we say 26.67 multiplied by 150, you will see that it will give you 4,000. And this is the span that we have used. So if we go and use 26.67 multiplied by 150, it will give me 4,000. Okay. So this is the span. This is the span used. Now I want to check what is the maximum span possible. Is this 150 sufficient for 4,000 mm, or it's going to be less? Now how to do that? We are going to use this equation. Now you can see that the limiting span by modification factor here is going to be 34.41. It means that I can say that span by depth, and I can say here maximum span. Let's say limiting means maximum, so maximum span by depth is equal to 34.41. Now the depth used is 150, so I can say that maximum span is equal to 34.41 multiplied by 150. So 34.41 multiplied by 150. You can see that the 150 mm can take the deflection of a slab up to a span of 1,000, let's say 161 or 160 mm. Okay. So once again, this 150 mm is okay to be controlling a deflection of a span up to 5,160. If it goes more than 5,160, you will see that this depth is not sufficient. I need to go and increase my depth. Now my span is only 4,000, so it should be fine. Okay. This is another way of understanding it. So you can either compare the span and the span, or you can compare span by effective depth. Both of the methods are the same. Now the question says, if you notice, I have used a ratio of 23, and 23 is not available in your code. Okay. 23 is not available in your code. Now from where did we get this 23? Now if you want to literally use the code, if you want to literally use the code, then you should either use 20 or 26 or 7. But if you want an accurate result, you're going to use 23. And the explanation of that goes to so I'm having 4 scenarios. I'm having first scenario, then I'm having second scenario, and then I'm having third scenario, let's say continuous. Okay, so we had 4 scenarios. Scenario number 1 is a cantilever. Scenario number 2 is a simply supported. Scenario number 3 is a fixed or a continuous supported element. Okay, and then we have one which is having one discontinuous and one continuous. Now, if you see here, the maximum bending moment in this scenario is WS square over 2. Okay. Maximum bending moment is WS square over 2. So moment is going to be WS square over 2. What about this scenario? The maximum bending moment to be WS square over 8. Here, the maximum scenario, if it's fully fixed, going to be WS square over 12. So here it's WS square over 12, and here it's WS square over 24. Now you can see this. You can see this is going to be having a bending moment here, a negative bending moment, and then negative bending moment like this. Or let's say here 24. Okay. Now if you see here, now you have studied that deflection is an equation of moment divided by EI. Okay. Deflection is measured in an equation of bending moment divided by EI. Now if you see which one of case number 1, case number 2, and case number 3 is having a higher bending moment. Can you tell me which one of those are going to be having the highest bending moment? Is it case number 1 or case number 2 or case number 3?
1.
Case number 1, because you see your WL square value is all over the same. WL square value is the same. First case we are only dividing it by 2, so the value is huge. Case number 2 we are dividing it by 8. Case number 3 we are dividing it by 12. Okay. Now what does it say here, or what does it imply? You can see that whenever the moment increases, your deflection is increasing. Now when your deflection is increasing, will the support be close to each other or far from each other? Once again, we said that moment is related to deflection. Whenever moment is increasing, deflection is increasing. Now to avoid deflection from happening, shall I keep the supports near to each other or far from each other? I have
closer to each other.
I have one, what you call, let's say, do you know the, what you call, do you know the barking, let's say, barking chains, سلاسل اللي يخليهم قدام المواقف. Do you know them?
Yes.
Okay. So we are having one rod here. Okay. And then we are having another rod here. And there is one chain. And you can see the chain is hold from here till here. Now, if I don't want this chain to reach to the ground, what shall I do? Shall I make the support closer or shall I make them far?
Far.
Okay. Now, if I want to reduce a deflection, what shall I do? You will see that if I want to reduce the deflection, I'll bring another pipe here, and then this is going to be my deflection. Do you agree?
Yes.
You can see that the deflection in this scenario is different than deflection in this scenario. Is deflection is different from the deflection in the other scenario. Do you agree?
Yes.
Okay. So now to avoid the high deflection, the code has given you a certain limit. Okay, the code has given you a certain limit of ratio. Okay, the code has given you a certain limit of ratio. Now, if you remember, we said span over depth equals to modification factor into ratio. Now, what happens if I want to calculate for span? You will see that your span equals to modification factor into ratio into depth. Now, if we leave modification factor and ratio and depth, you will see that whenever we increase the ratio, your span will be increasing. Do you agree? Do you agree whenever we increase the ratio, the span will be increasing?
Yes.
And do you agree whenever we increase the span, the bending moment will increase? Span is L. So do you agree that your L will increase?
Yes.
And if your moment is increasing, do you agree that your deflection is increasing? Okay, so once again, if we increase the ratio, span will be increasing. If the span is increasing, moment is increasing, and then eventually deflection is increasing. So the code what have done, they limited the ratio here. As I said for you, if you are going to use cantilever, okay, if you are going to use cantilever, we are going to allow you only to use a ratio of 7. Now, ratio of 7 will give you what? It will give you a lesser span, which will give you a lesser moment, which will give you a lesser deflection. Okay, because the moment equation here or the coefficient is very high. Now, what about simply supported and what about continuous? You will see that for simply supported is a little bit better than the cantilever. We are dividing our moment by 8. So the code says for you. So the code says for you that this is going to be 20. So now I'm allowing you to go for longer span. Okay. Now once again, whenever we increase the ratio, span will be increasing, and then moment will be increasing, deflection will be increasing. Now what about the third scenario? You will see that the third scenario is having a lesser moment. So this is higher, and then this is higher. Now we have m is equal to w square over 12. It means that because of the lesser moment, we will have lesser deflection. Because of the lesser deflection, we can have longer span without having huge deflection. So the code says for you, if you are using continuous, then your coefficient is, or your ratio is 26. Now, have you understood from where these 7, 20, and 26 came? Or what is the concept behind 7, 20, and 26? Once again, they are related to how much bending moment and how much deflection the element can have. So for a cantilever, the bending moment is already high. To avoid high deflection, we are limiting the span. We will not let the cantilever go for a long span. Because if there is a long span, there will be a higher bending moment and a higher deflection. Simply supported, it has lesser bending moment than a cantilever, so we can go a little bit longer in the span. That's why you can see the cantilever is having always shorter spans. Why? Because they will deflect a lot. Simply supported is a little bit higher. Continuous is a little bit higher. Now, if you go to this scenario, you can see that it's a combination between case number 3 and case number 4. It's not case number 2, and it's not case number 4. You cannot have this WL square over 8, and you cannot have this WL square over 24. This will be somewhere in the middle. Okay, this will be somewhere in the middle. So rather than taking it as 20 or taking it as 26, because once again, if the moment is different from case number 2, you cannot use it to be 20. If the moment is different from case number 3, you cannot use it to be 26. So the optimum thing is going to be using the average of case number 2 and case number 3. That is going to be 23. Okay. Now, if you want to use the logical answer, then your answer should be 23. The other codes which are elaborating the DS codes have used it to be 23. Now, if you don't want to use that later on in your job, and you have been asked to fully use the BS code, then you should be using 20. Okay, I cannot use 26. Once again, this can take, for example, a span of 5 meters. This can take, for example, a span of 7 meters. Okay, this can take a span of 6 meters because it's in between 2 and 3. So if I want to design it, I'll not go and design it for 7 meters because it will fail. I will be designing it for 5 meters only. Okay, so once again, you're going to be using it 23. If one side is continuous, one side is discontinuous, you're going to use it as 23. If literally later you want to go and use the BS code in your job and not your logic, then you can have it as 20. Once again, from where we have got this, we have got it from the drawing, from the first scenario, from the first diagram. Now, if we see the diagram, now are we designing always for X or for Y? The critical is X or Y. The critical is X or Y. The critical, you will see that it's always X, where it has a highest value as well. Now you will see in this X, do we have both supports discontinuous or one continuous and one discontinuous? For X, always you are checking for X. In this scenario, are the supports both of them continuous or both of them discontinuous, or one is continuous, one is discontinuous?
One continuous, one discontinuous.
Okay. So if both of them for X, both of them are continuous, then you should be using 26. If both are continuous. If both are simple or discontinuous, then you should be using it as 20, because both supports are simple or discontinuous. Now, what about one continuous and one discontinuous? You should be taking the average of both, so you should be using it as 23. That's why we have used 23 for this case. Okay. Now doing that, we can check why we have used 23 now. Why we have used 23 here? Because one support for X is going to be discontinuous, so the other support is continuous. Okay. And we checked, and I told you can calculate it in terms of span by effective depth, or you can compare between a span to a span. My maximum span that I can be taking is 5,160. How much span is available now? 4,000. So I'm lesser than the maximum span. If I exceed 5,160, you will see that your element is going to deflect more than the required value. So one of the semesters I have asked the students to calculate the maximum possible span. So in order for you to calculate the maximum possible span, you need to use the equation of deflection. They will be controlling, as we said earlier. We said bending, shear, and deflection. We said deflection is a critical failure in slabs. That's why you need to take deflection into account. Finally, we are going to draw the detailing. Now, if you remember, we used to have X. We are having the reinforcement of X, which is represented by the white color. And then we have placed the second bar, third bar, and whatever. So these are reinforcement of X. Now, are they in the bottom or are they at the top? Now, I have drawn for you a longitudinal section, and I have drawn for you a plane. So this is a longitudinal section, and this is a plane. Now, in the longitudinal section, can you see the white one is representing the bottom or the top?
Bottom.
Bottom. Okay, so they are representing, or it's representing the bottom. Now, is it parallel to X or parallel to Y? If you remember, we said that it's not to the scale, but anyhow, this is my X and this is my Y. So the white color is parallel to X. So you can say that this is X positive, or whatever we call it as ASX positive. It is the reinforcement of X. It is bottom, so it's positive. What about the other one? The other one is a black color, which is parallel to Y. So in this scenario, this black color, is it in the bottom or top? It is in the bottom, so it is going to be ASY positive. It is parallel to Y, so it's Y. It is at the bottom, so it's positive. And you can see that these are the reinforcement of Y. Now, do we have any top? Do we have any top reinforcement? If you remember your bending moment was like this in terms of X. Okay, so we don't have bending moments here. So that's why we don't have top reinforcement here. But in this scenario, we have bending moment. It means that you should be having reinforcement at the top. How to represent that? We are having a reinforcement which is shown in red color now. Now, the red color, you can see that it's parallel to the white color. Okay, it's parallel to the white color, or the same line, you can see. Now, since it is in the same line or parallel to X, then we are going to say that this is going to be ASX. Is it negative or positive? It is going to be negative because it's at the top. Now, what about the ASY negative that we have calculated? ASY negative is going to be coming here. This is the red color. ASY is going to be coming here. So this is the continuous part where we are designing for the negative bending moment here. Okay. Now these are representing ASY because they are parallel to Y. Negative or positive? Negative because they are in the top. Okay. Now this is the explanation of your detailing. Of course, you need to mention that the depth is 175 when you draw. Okay. When you draw, you are required to specify everything, even the span. How much is it? That this is going to be 4,000 mm. Spacing of the bars, everything you need to mention. Okay. And normally we write our reinforcement in terms of in this way. We write it as 10, for example. We are using for ASX negative 10 mm diameter. So we write 10 diameter at, for example, 225 mm center to center. ASX positive, it is going to be 10 mm diameter we have used at spacing of 300 mm center to center. And it goes on for the other reinforcement. Okay. Doing that, we have finished today's class. If you have any question, you may ask. If you don't have any question, then you are free to leave. By the way, your quiz number one is going to be okay. Your quiz number one is going to be on Thursday, 11th of March. It's not going to be 10th because some students are having clash with other course, a clash with another course. So your exam is going to be 11th, and your midterm has been already announced that it's going to be on 25th. Okay. So 11th is going to be your quiz one. After 2 weeks, you are going to have your midterm. Both of them are on Thursday, 11th and 25th. Any question?
Mr.
Yes.
Which time quiz?
I'll let you know. The quiz is going to be evening only. Evening, maybe after 4, to avoid any classes for the students.
Okay, Mr.
Any other questions that you are having?